Hello everyone. Today let's solve a question in physics which is a combination of the chapters magnetism, rotation and circular motion. So let's read the question. A solid sphere is held at rest on a fixed hemispherical bowl made of insulating material such that the center of the sphere lies on the bowl's horizontal diameter as shown in the figure. They have given the mass of the sphere as 252 grams and charge is 0.51 coulombs, and which are both uniformly distributed. Also, they have told that there's a uniform magnetic field into the plane. So we have to find the limiting value of B, that is the magnetic field in Tesla, so that the sphere does not leave contact with the ball in its course of motion once released. Also, they have told that we can consider contact surface to be sufficiently rough, which means the sphere will undergo rolling motion, perfect rolling motion, and the hemispherical ball can be considered as non-magnetic. We have also given capital R of the ball as 10 centimeter and radius of the sphere small r as 3 centimeter and g is 10 meter per second square. So the data in the question is mass of the sphere is 252 grams, that's 0.52 kg. The charge is 0.51 coulombs. The radius of the hemisphere capital R is 0.1 meter. The radius of the sphere small r is 0.03 meters and g is 10 meter per second square. So try it out and I will give you the solution. I hope that you have tried the question. Now I'll discuss the solution. So when we release the sphere from the topmost point, it will undergo pure rolling motion. So let's take the velocity v and angular velocity omega. Now let's consider two points dq and dq which are opposite to each other. Each dq has a velocity v due to translation and a component omega r due to rotation. If we try and find the magnetic force direction of each dq, we will see that the force component due to just the velocity v of both the dq's will be in same direction and will add up, but the magnetic force component due to omega r of both the dq's will be in opposite direction and will cancel out. So the net force can be said just due to the translational velocity of the sphere. So this is the point. Now let's look at the FBD. So this is the hemisphere with radius r, capital R, and this is a sphere. It has a velocity v towards the right and angular velocity omega, and this omega we can write as v by r because it's pure rolling motion. It also has mg downwards and fb upwards and normal reaction also upwards. FB direction you can find using Fleming's left hand rule, taking velocity towards the right and b into the plane. So now let's write the equations. When we write energy conservation, the change in potential energy mg capital R minus small r, because initially it was at the top and then it's come here. So the center of mass is displaced by capital R minus small r. So change in potential energy is equal to half mv square, that is the translational velocity, plus half I omega square, that is the angular kinetic velocity. So, and also of the solid sphere, moment of inertia is 2 by 5 mr square. So when we substitute the values, we will get this, and substituting the value of g, capital R and small r, we get that v is 1 meter per second. Now, when we apply circular motion, because the sphere is in circular motion in the hemisphere about the point O, so FB plus N is upwards minus mg, that is downwards, is equal to mv square divided by r minus r. This is the mv square by r, and the radius here is capital R minus small r, because we have to consider the center of mass to be performing circular motion. So FB is QVB plus N minus mg is equal to mv square into r minus r. For limiting case, that we can take n equal to 0 as they are told to find the minimum. So this is all the calculation. So after calculation, we get B is 12 Tesla. So this is the answer. I hope that you too have got this. Thank you.